So this talk brings forward a kind of a program that we had in the last few years at the Laboratory for Web Algorithmics in trying to understand the behavior of centrality measures, at least of classical centrality measure, with respect to certain changes to the network, with the idea of trying to understand whether these centrality measures are sensible, like going beyond anecdotal evidence like looking at the top results, or general theorem for which is very difficult sometimes to understand what actually the centrality does. Because the big question is very simple. You have some notion of centrality on a directed graph, and you had the new arc from x to y that wasn't there. Okay, so the question is very simple. And it is what happens. What happens when you add an arc from x to y? You might ask several things to happen in this case. One of these quite simple is score monotonicity. That is, when I add an arc towards y, the score of y increases. Which, if I'm trying to define a measure of importance, seems to be fairly reasonable. Okay? Actually, this appears in a paper by Sabituzzi in 1966. So this kind of question has been asked for a long time, but nobody that we know tried systematically to answer this kind of questions. We studied this in Axiom for Centrality, which is a paper that I say with pride, widely circulated and is used in several courses on neural networks, on networks, not on neural networks. Okay, we get a table a little bit like this. So you know what is degree, closest, harmonic, centrality has been somehow nominated. I will talk about them. Celia will talk about that. Betweenness, you know, page rank, eigenvector centrality, cat, the singular vectors, salsa, if you don't know what it is, it's okay. But mainly notice that is mostly no, okay? And so these no, for the most part, actually come from the fact that we're considering red, very general graphs. So almost all these no come from taking a click to isolated nodes and try to add an arc between the two isolated nodes. So all this kind of ranking will not increase the score of y for various reasons, depending on the fixed point of linear operators and so on. Maybe it's a little bit unfair because people trying to use like eigenvector centrality think that the graph should be strongly connected. So we are being very mean. Not only this is really not enough, because score monotonicity, what it really says is that something good happens. So I add an arc towards y, something good happens. The score of y increases. But we need another axiom that says that nothing bad happens. Because maybe, yes, I add an arc towards y, y increases in score, but then for some mysterious reason, another node z that has nothing to do with x and y, which was below y, suddenly goes above y, which is totally crazy. Okay? So we need something that says that nothing bad happens. A little bit like consistency and completeness in logic. Okay? Consistency is something good happens, coherence, is nothing bad happens, completeness is something good happens. And doing the two things is much more difficult. So imagine to rank the node by score. So you have your centrality on the graph, and you list the node by score, and you number them, 0, 1, 2, 3, 4, and you number ties with the same number. So if some node has the same score, they get the same number. Okay? What we want to say is that the rank of y, so not the score, the position in the rank, cannot decrease when I add an arc towards y. So I cannot worsen the position of y in the ranking of the node by adding an arc towards y. Seems reasonable, does it? Okay. Let's make it formal. I'll make it formal. It's a bit ugly. So what this says, by the way, this appears in a paper by Ravi and some other people, Internet Mathematics 2004. So this is the making concrete definition with the rank. So it's a bit ugly to read. So essentially it says that if x had a score less than or equal to y, then the new score of x must be less than or equal to y. And if x had a score strictly less than y, then it must have a score that is still strictly less than y. But the meaning of that is exactly that the rank does not decrease. Okay? We call this loose rank monotonicity. This was actually called rank monotonicity in that paper. The paper proves score monotonicity and loose rank monotonicity for page rank under the assumption that the Markov chain is regular. So it's ergodic, works very well. So this kind of question has been asked for 12 years at least. We are also interested in strict rank monotonicity, which is a little bit stronger in that we want that if x had a score less than that of y, then it becomes strictly smaller, which means that not only y does not decrease its rank, but all ties with y are broken in favor of y. So if y was in a tie with several nodes, they had the same score, and an add-on arc towards y, it must go above them. Okay, this is a stronger statement, of course, than the previous one. So what I'm just trying to do now is to guide you through a big table that has 4 columns. So on the left, red part is general graph, and the blue part is strongly connected graphs. Okay, and we want to fill this table. We actually filled this table, but it's interesting to see what happens while you fill this table. Now, just as a warm-up, degree clearly is perfect, is rank and score monotone. When I add an arc towards y, is degree in degree, increases, and any node, it was in a tie, so at the same in degree, now it's above them, okay? So the star means strictly rank monotone. If there is no star, it's loosely rank monotone. So, okay, what do you believe about betweenness? Any opinion? Raise your hand. Betweenness is rank monotone. Come on, guys. It's not rank monotone. Okay, I know that was too easy. Okay. Betweenness, as the previous speaker said, betweenness is actually a measure of robustness or, passage through the node. It doesn't really work well as an importance or centrality measure, and indeed, if you try to do the betweenness of the Hollywood co-starship graph, you get completely crazy results. The first 10 people are completely unknown guys. You don't even get George Clooney. It's really painful. This is a very simple example of explaining why nothing works. And the reason is that if you look at this example, you will see that adding that arc, you are increasing the shortest path through x and not through y. So when I add that arc, there are 2, 3 what is that? Okay. There are 2 shortest paths from the lower, I'm lost, what I'm doing. Okay, there are 2 shortest paths from the bottom node to the top node that are shortened, but none that go through y. So essentially, there is an inversion of rank. It goes exactly in the opposite direction, but it's just because the measure is not devised to do centrality, it's just devised to do to count the number of paths. And when you add an arc, not necessarily you increase the number of paths in the target. Maybe you increase the number of paths in the source. So, okay, this was easy, but doesn't tell really much about betweenness. Betweenness is perfectly fine. Just don't use it as a centrality measure. Okay, this starts to be interesting. Closeness versus harmonic. Everybody knows that we love harmonic centrality. So, closeness, everybody knows what is closeness. Who doesn't know what closeness is? Raise your hand. Oh, I cannot do this question, of course. Okay, so on the left, you have closeness centrality. So you take a node x, you add the distance from all other nodes, and you reciprocate. So if it's high, means that the sum of distances is small, so the node is very central. Essentially, you're taking an arithmetic average of distances, modulo some constant factor. On the right, you're adding up the inverse distances, so you're taking a harmonic mean of distances instead of a arithmetic mean of distances. And we already know that this is score monotone and this is not on general graph. So if you don't have a strongly connected graph, certainly on the right is better than on the left. But for general graph, this was left as there was a big question. The point now, however, is that closeness is loosely rank monotone, while harmonic centrality is strictly rank monotone. So even on strongly connected graph, harmonic centrality behaves better. And why it might seem a little bit weird, the counterexample is totally trivial, so let me discuss it. So forget the dashed arrow. This graph is symmetric, so y and z have exactly the same centrality, because the sum of shortest path in y and z must be the same. Okay? Now, what happens when we add an arc from x to y? Okay, there is a 2 path that is shortened to 1. So the denominator of the score of y will decrease by 1. And then there is a 3 path to z, which will be decreased by 1. So by 3, it becomes 2. Exactly the same change. So they will remain exactly the same. Think of Twitter. You have a centrality on Twitter. There are two people with exactly the same centrality. You add the follower. They remain with the same centrality. Good or bad? Clearly bad. Okay. You should have said bad, but. So loose and strict rank monotonicity actually make it possible to easily make a difference between harmonic versus closeness centrality, even on strongly connected graphs. Okay, so we are filling the table. So closeness doesn't work at all in non-strongly connected graph, works reasonably on strongly connected graph, but harmonic is doing so much better. Seeley's index, this is easy, the stationary state of the uniform random walk on the graph. You could call it page rank without the damping factor, but since it's divided 60 years before, maybe 50 years before, let's name it in a different way. This is score monotone and loosely ranked monotone on strongly connected graph, and actually it's proved in that paper because while the paper concentrates on page rank, all the proofs are done in general for a regular Markov chain, which is what's happening here. And the reason why you cannot improve to strict is due to the very nature of Markov chains. So if in a Markov chain you have a node without degree 1 followed by a node within degree 1, no matter what you do on the rest of the graph, the stationary state of the two nodes will be identical. And no matter what you do, because the stationary state equation says that the probability of Z is exactly equal to the probability of Y. So you can fill as much as you want, make the graph bigger, whatever you want, but as long as Y is out degree 1 and Z is in degree 1, they have the same score, which means that when you add an arc from X to Y, because of that theorem, the score of Y increases, but the score of Z increases exactly in the same way. So here we have the same problem of closeness. Rank monotonicity is not strict. Oh, by the way, if you know rank monotonicity from voting theory, this is exactly the same thing, okay? Rank monotonicity in voting theory is that if a user changes his mind and raises up a candidate, the candidate cannot go down in the global score. It's exactly what we're doing here. It's just on graphs instead of people that vote. Okay. So Seeley index go to with closeness with stuff that works only on strongly connected graph and not that good. Okay, page rank. This is also interesting in my opinion. So page rank was, as I said, proved score monotone and loosely ranked monotone, given that the Markov chain is regular. And what we were able to do is to prove that it is strictly ranked monotone, given the scores are non-zero. So there are weaker hypotheses and a stronger thesis, but we used some deeper result for the theory of M matrices. And okay, I will make a very bold statement. Lesson learned is that page rank is not a Markov chain, in the sense that, of course, it is a Markov chain, okay? But there are things that are true of Markov chains, that are false of Markov chains, general Markov chains, that are true of page rank. So at some point, you hit a wall in which you cannot go through with the general theory of Markov chain. Of course, if you divide the theory of Markov chains built on a convex combination of a constant chain, maybe you can get to the same result. But my observation is that it appears to be much easier using M matrices and in general linear algebra. Okay? So, sorry? Oh, M matrices are matrices that are, okay, it's like 1 minus alpha, a positive matrix with alpha less than the spectral radius of the positive matrix. It's I mean, the matrix of the 1 minus alpha M matrix of page rank is an M matrix. It's a very well studied. There are billions of papers. The linear algebra has spent 30 years publishing papers on M matrices, so we have a lot of material. Okay, we are almost. Okay, I mean, how much do I have? Because I didn't. Of course, I didn't look at the time when I started. That's the usual thing I do. 10 minutes. Okay, I can do it. Okay, the dominant eigenvector, also called eigenvector centrality. This is always very old stuff, and Katz's index. I'm putting this together because it's less slides. So in general, the left dominant, okay, everybody knows what the dominant eigenvector is. I give it for granted, and it's like eigenvector centrality is very common. You might not know the combinatorial characterization, which sometimes helps. So you can define eigenvector centrality without using eigenvectors. Okay, so just take a node, you take the number of incoming paths of length 1, 2, 3, 4, you get a growing function. Okay? You do it for every node, so you have a vector whose coordinate grow with k. And you normalize this vector, and this vector we stabilize to the dominant eigenvector. So the dominant eigenvector measures the relative growth of the ball of incoming path in each node. It can be defined in a totally combinatorial way if you're not at ease with linear algebra stuff. Is not rank monotone and not even score monotone general graph, but works very well on strongly connected graph, which explains its success in several areas, but don't use it if the graph is not strongly connected. Cut-seed index is basically page rank without normalization, so of course it works like a charm, exactly like page rank. That's not surprising. In fact, we prove strict rank monotonicity for a wide class of damped spectral ranking, in which you have a matrix M, a damping factor, and you do that summation and multiply by preference vector, which can be written also in that way using the linear operator. So if M is the adjacency matrix of the graph, this is Cut-seed index. If M is normalized by rho, this is page rank. If M is something else, this is a damped spectral ranking of some kind. It might be interesting to have a look at why even rank monotonicity fail horribly for dominant eigenvectors, okay? So if you take this graph and you try to compute the dominant eigenvector, all the rank goes to the 3 loop because all the arrows are in this direction. So there's no way rank can flow back to Y and Z. So when the dashed arc is not there, you get all of these 3 elements have the same value and these have 0. Now the point is that when you add that arc, you expect the rank of Y to not decrease. But there's a trick, because when you add the arc towards Y, you do something extremely destructive. You make the graph strongly connected. So suddenly, there is rank everywhere. But we built the example so that Z is locally more dense than Y. So even if the new arc goes towards Y, Z gets a higher score than Y. So even in this very simple example, we violate rank monotonicity as the original graph is not strongly connected. And we are basically here. I hope you can use this table once in your life for something. I mean, I think it's a nice table. Okay, right dominant singular vector. So this is the left dominant vector of ATA. There are many ways to look at this. I will use the HITS view from the Kleinberg algorithm for web pages. So the idea is that you have a graph of web pages and you're trying to compute at the same time 2 different scores, the authoritativeness of a page, so how much the page is good, and the hubbiness of a page, so how much the page contains good link to other pages. You do this by a ping-pong process. So we start with a constant authoritativeness, and then we compute the hubbiness by adding the authoritativeness of the pages that point the hub, because a hub, sorry, I inverted the arrows, right? Yes. To compute the hubbiness, we add the scores of the pages pointed by the hub, because a good hub points at good pages. But then we recompute the authoritativeness by adding the score of the hubs that point the page, because good hub point to good pages. We go in this way, iterating with a mutual reinforcement of the 2 concepts, and we get 2 vectors, the left singular vector and the right singular vector, which we'll discuss the left one, which is the right one, which is the left dominant eigenvector of that matrix. That's a T. The slide should have a T there. I don't know why there is a single. Oh, well, whatever. I must have moved ATA. In social sciences, the same is done with groups and people. So you have people and groups. You want to score people and groups. So you start to score people, and then good groups contain good people. And then from the good groups, you can compute a score for people, because good people will be belonging to good groups, and you do ping pong in the same way. But the basic idea is this mutual reinforcement. Unfortunately, the singular vector fail all monotonicity axiom, even in a strongly connected graph. And so this is the ugly example. Basically, what happens is that before adding the arc, there is a score only on the click. But as soon as we add an arc, as in the previous example for the dominant eigenvector, we get score everywhere. But at that point, Z is locally much more dense and hits, I mean, the right singular vector in general, has this tight community effect, because so that if you have a local tight community, it gets all the scores. So even if you had an arc towards Y, Z get a greater score. So in even on strongly connected graphs, we don't get score rank monotonicity. Also, it has a path characterization in case you don't want to know the linear algebra. So you start from a node, and now you count the zigzag path. So you start from a node, and you go backward, forward, backward, forward, backward, forward. For each 2k, you count the number of zigzag paths of length 2k, and then you measure the difference in growth of this function for each node. And from that, you get the singular vector. So now we're here. I won't define salsa because that will take definitely too much time. But it's another score based on a kind of singular vector made. It's like hits plus page rank in some sense. I mean, it's plus Markov, okay? But also in that case, we don't have any of this any of this behavior we would like to have. Okay, so the table is there, the paper is out. So I don't know if the paper is out actually, but the table is there. So we found this very fun to do because rank monotonicity provides yet another perspective on centrality. And well, first sharply divides closeness from harmonic centrality, which we actually like, and suggests that M-matrix theory should be able to prove stronger results for page rank than just Markov theory. Now, if your favorite centrality has some no, don't despair, because it might be true on a perfectly sensible, a little bit smaller class of graphs. For instance, when you look at the singular vectors, the point is that we are dividing between strongly connected graphs and non-strongly connected graphs, okay? But because of the nature of this centrality, which has this zigzag path, what really counts is not that the graph is strongly connected, but that ATA, seen as a graph, is connected. And the two properties are completely independent, okay? So we can build this counterexample because actually, when you go and when you see ATA taken as a graph, forget the numbers. ATA is 3, 4, 5, take that 0 and 1. ATA in this example is not connected. My hypothesis is that if you restrict this to ATA which are connected, everything should work fine. But I mean, the divide in this paper was between strongly connected and non-strongly connected. So we followed the line we use with all the other centralities. That's it. I hope you like it. Questions? Coffee break. It's a couple of pages. Is maybe a little bit easier than in your paper. I wouldn't say is incredibly easier than in your paper, okay? Is a little bit shorter, and you can prove a little bit slightly stronger result, but yes, it's not incredibly easy. You need to tweak a little bit. Okay, thank you again.